In this video, I'm going to demonstrate logistic regression using the IRIS dataset. So the IRIS dataset is kind of considered like a hello world for machine learning. It's a common dataset to use. It has 150 records of 3 different species of iris. And so we're going to start by talking about what logistic regression is, and then we'll open the IRIS dataset, access it, graph it to visualize what the data looks like and see if it's a good fit. Then we'll pre-process it to get ready for regression. We'll divide it into a training and a testing data set, and then we'll create and validate the model. So first of all, logistic regression. What makes that different from linear regression? Linear regression is looking for a continuous variable result. Something like percent of people who might vote for a candidate, or average amount of add to carts, or something like that. Where logistic regression is really looking at categorizing information. And in this case, we're trying to categorize irises into the correct species. So let's jump right in. I've started our notebook with imports that we'll need for this example. And I already have loaded the IRIS dataset locally onto my computer as iris.csv. So let's go ahead and read it in and take a look at the top 5 rows. And we have sepal length, sepal width, petal length, petal width, and then the species. Now this is an ideal case of logistic regression because it's how the Linnaean classification system is organized. Kingdom, phylum, class, order, family, genus, species, the way that living things are organized. Now this was developed by Carl Linnaeus many years ago by just looking at the physical attributes of plants and animals and living things and saying, okay, we can classify similar things together. That's a good analogy for what we're doing in logistic regression is let's look at these attributes and then let's see how we can put them into a certain classification. I spent a lot of time traveling and photographing plants as I traveled and had a lot of fun with that. And sometimes you're lucky and you get a label for a plant and you know exactly what it is. But other times, you just had to go back to this classification system and remember that, say, a mugo pine is a shrub-like pine, so it's not going to get very tall. And then for the taller pines, you count things like the needles on a bundle, and is the needle twisty or not? And these are the things that will classify a species. So this is where I think a couple things will help. First of all, what are the species that are available in the data set? And we can find that by using this value counts operation on that species column and then say, okay, how many do I have of each? And in this data set of 150 rows, I have 50 of each. Now, let's look at some of the columns that I've identified above with irisDF.columns. And let's graph these for each species and see if we can pick up any kind of similarities or any kind of grouping. So I start with sepal length, and you see on average there's a certain difference in the sepal length from 5 to greater than 6. Let's do this for the other attributes as well. Sepal width, again, a little distinction on the average, which is helpful. Petal length, a definite distinction there on the mean. Now let's take a look at petal width. If you notice here, I'm just taking our data frame, grouping by species, grabbing this column, which in this case is petal width, asking for the mean of that, and then doing a bar plot. Since I'm grouping by species, that's why you see 1 bar for each species. And you notice, of course, it's taking the mean. So petal width, definite differences there. Now the trick is, though, we're looking at mean. What might be a little more interesting is doing a box plot, because we can take a look at the entire range of values and their outliers, and we can see how much these overlap. If there's not a whole lot of overlap, then we've probably identified a good feature to use in regression. So for a box plot, I simply use the data frame and then call the box plot function on it. I indicate which column I want to use, and by species will be the grouping. And then I set a label if I wish. And here we have sepal width, and you see, okay, we have the basically the range bounded by these 2 lines here, and then the 25th percentile the 50th percentile and the 75th percentile here. So we see there is maybe a little bit of overlap on sepal width. So we'll continue this with the others as well. Sepal length. And the setosa is down here. This one looks like this is going to be easy to identify. The versicolor and the virginica maybe a little bit closer. Petal width. This one looks like a fairly good identifier at normal. You do see the setosa. We have a couple circles up here, which indicates that there are a few outliers. We could take a look at those and see if that's data that we want to consider, if we'd like. At this point, with just 2 outliers, I'm not terribly worried about it. And petal length. So once again, setosa out on its own, the versicolor and the virginica differentiated, but there is a bit of overlap. So I'm going to do some scatter plots in just a moment so that we can see, do any natural groupings emerge, which I think we probably already got the idea from these graphs. But first, I want to clean the data a little bit. Typically, when we're doing regression, the features that we're going to use to predict the target are x's. x1, x2, x3, and then the target is a y. And so I want to rename our columns so that it will be consistent. And sure enough, you see x1, x2, x3, x4, and L. Okay, so L is our feature here. It's what we're going to predict. And a consideration is that, remember, we're doing logistic regression, which is going to put things into categories. But the trick is that it requires some mathematical model for that. So, okay, we can't say this equals setosa, virginica, or anything like that. What we have to do is we have to encode the target so that it equals a number. And we can do that with label encoder. We can start with by creating a label encoder. And then let's see what it comes up with when we ask it to take a look at that L column. It says, okay, I see iris setosa, iris versicolor, iris virginica. And we say, okay, those are words, but we want to make them into numbers with a unique number for each unique word that we have there. So I'm going to say LE transform, and we see that now it has split our species into numbers 0, 1, and 2. Well, we want to save that back into our data set. So I will say irisDF, and we'll use that L column, equals LE transform, just as I typed above. And then let's print out irisDF. And we see now in that L column, instead of having words, it has numbers, so that's going to work a little bit better for our formula. Now I'm going to put together a scatter plot matrix where it's going to do something a little bit interesting. Let's see what's going on here. We're plotting one feature against another. And then each of the plot points is going to be a different color based on the species that we're plotting. And this actually kind of works out really well. We've done the label encoder. We know our species are now either 0, 1, or 2 instead of setosa, versicolor, and virginica. Because they're numbers, we can pass them in to the C argument here, and it will assign a unique color based on that number. So let's see what we get here. Well, the purple is kind of in a group by its own, and we noticed the setosa many times was by itself. There was a little bit of overlap in the versicolor and the virginica, and you especially see this in this top left graph. But in some of the other graphs, you start to see a little bit of distinction. There is still some overlap, but it comes a little more distinct depending on what feature we're actually graphing. And now comes the fun part, which is building our regression model. One thing to consider with regression is that it helps if everything's at the same scale, because we're trying to predict something based on a series of numbers. So if you have age, weight, number of miles between here and your next big city, that number of miles is going to be on a way different scale than age and weight, potentially, depending on what city you're going to. But we want to be able to scale things. And a lot of times that's where the scatter plots are handy too, because we can see if there's some kind of natural rhythm to how things fit together, like an exponential curve that we could scale with a logarithm. But this is a bit of a simpler case, so we're just going to use the standard scaler. And we see, okay, we're scaling everything except the column that we're trying to predict. And we see, oh, okay, these numbers are starting to look like they're of a similar scale. Next, we're going to divide the data set into training and testing. So we use this train test split function to say take our scaled data set, which we created up here. Notice irisDF scaled equals scalar transforms. That's where we're creating that scaled data set. And then we're trying to predict the L column. And we want the test size to be 0.3, which means we're going to reserve 30% of our rows for testing, random 30%, and 70% to build the model. Now this actually returns 4 different values for us, an X and Y training and an X and Y testing. Next, we will instantiate our logistic regression, save it into this thing called model, and then say model fit. And that's where the magic happens. That's where it says, okay, given these X, how can I predict these Y? Note what happens next, though. After we build the model, we tell it to predict those 30% of records that we held aside for testing. And then that's going to give us a way we can validate our results. So 70% to build the model, 30% to test. Well, for that 30%, because it comes from this original data set, we already know the species. So we can have the model predict the species and then say, okay, how good were your predictions? How do we know how good the predictions were? Well, one thing we can do is come up with this confusion matrix where we start off with our Y testing data set, the Y testing predicted, that was the predictions that came out of our model, and then we put together a little diagram like this. And basically what we have here along the diagonal are the true positives and true negatives. In other words, what was predicted accurately. What we have on the others, the darker ones that you see here, are false positives and false negatives. So in this case, just doing a bit of math in my head here, it looks like we have about 44 that were predicted correctly, one that was predicted incorrectly. So I'll say, yeah, that model was pretty good. There are several other metrics that we can get from this as well. Precision, recall, F1 score. I'm going to go ahead and plug those in, but I'm going to talk about them in a separate video. Just keep this one nice and concise. I'll have a follow-on video that does a bit of analysis of that. So we'll start with accuracy. And we see 0.977, quite good. Let's take a look at precision. By the way, notice I'm just invoking a function here called accuracy score. Passing in the necessary parameters. Here I'm calling precision score. And precision, again, very good, 0.97, it's about 98%. Take a look at recall and F1, and 97, 98% again. I've run this demonstration several times, and sometimes it comes to a high percentage, like 98%. Sometimes it comes to just perfect accuracy, 100%. A lot of that depends on how the model divides the train test split. You know, and does a versicolor or virginica that's on the fringe land in the testing or the training? But nonetheless, these numbers are about what I would expect for this data set. Now, can we use this model to predict other data that was not in this spreadsheet? Well, I came up with a little spreadsheet of my own here, where I took several of the rows that existed in that original CSV file and just tweaked some numbers just barely. But then I also added one of my own down here that I just made up, and I'm curious to see how it handles that. So we'll go ahead and read in that file with our normal read CSV, and we see, sure enough, the file's there. Now we have to repeat several of the steps that we did up above, like scaling and also transforming. So go ahead and take care of that. Now let's try to predict what the species is for these values. So I go back to the model that we created. Remember, model is a variable of type logistic regression. It's the variable I instantiated up above. And I'm simply saying, okay, let's take this my irisDF, which is that smaller CSV, and let's try to predict what we get out of that. Let's take a look at what it came up with. And it said setosa, 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 versicolor, 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 virginica, 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 and then finally setosa. So for that final item I made up, we have sepal length of 5, sepal width of 3.4, petal length of 1.5, and petal length of 0.3. So you see those two, these two values here, they look a lot more like a setosa than a versicolor or a virginica. Very small petal and petal length and petal width. Of course, we could go up and look at the bar chart and confirm that the setosa has the smallest petal length and width. And I'm going to say, yeah, it did predict it right. Now, how do we know that the 0 is a setosa? Well, for that, we have to go back up to where we did the label encoding. And remember, we had a bit of output there where the setosas are the first 50. So those are the zeros. And then the versicolors are 1 and the virginicas are 2. So if I apply that back to this result, I say, yes, it did correctly predict it as a setosa. And that is a look at logistic regression with the IRIS dataset and a little bit of things we need to do to look at the data, investigate the data, pre-process the data, rename the columns, do some scaling, divide into train into test, create a logistic regression object, pass that object the training data set, and then have it predict the testing data set, and then compare those predictions to the actuals and come up with our accuracy, precision, F1, and recall scores, and then use that same model to predict new data. So I love this topic, and I hope you do as well. I certainly hope you enjoyed this video, and I look forward to reading your comments. Thank you.